The Cherenkov telescopes that the CTA are built up of are designed to detect gamma rays, but they do this through detecting Cherenkov light. But what is Cherenkov light, and why don't the telescopes just detect the gamma rays directly? Let's start with the second question. Why don't the telescopes just detect gamma rays? Gamma rays cannot be detected from the Earth's surface. This is because they are absorbed by the Earth's atmosphere. The atmosphere is a thin layer of gas that surrounds the planet. It is a good thing that the gamma rays are absorbed, as they would be fatal for life on Earth. When the gamma rays enter the atmosphere, they collide with the gaseous molecules. Gamma rays are absorbed by the atoms and in the process dislodging electrons, which are negatively charged, and positrons, which are positively charged electrons. Gamma rays can be detected from outside the atmosphere, and there are instruments orbiting the Earth right now collecting gamma rays. But the CTA is ground-based, and we cannot detect gamma rays directly as they don't reach the ground. We can, however, detect the effect gamma rays have on the atmosphere. Cherenkov light is produced due to the gamma rays interacting with the atmosphere. To explore the origin of Cherenkov light, we will first explain how waves propagate. Waves are caused when there is a disturbance in a medium leading to high and low pressure regions. The easiest way to explain Cherenkov light is to start with water waves. Imagine dropping a series of stones from your hand into water at regular intervals, say every 1 second. When the stones hit the surface, they will disturb the water and produce a wave. As the stones act like point disturbances, concentric rings are produced from where the stones are landing. Now imagine this time, instead of dropping the stones in the same place, you move your hand along whilst dropping them. This will cause a series of rings to be produced. The rings produced from the earlier stones would have become the largest. As you keep dropping stones, the rings become bunched up in the direction the stones are being dropped. The amount of bunching depends on how fast your hand is moving and how fast the ring moves in the water. If your hand moves at the same speed as the rings, they will all bunch up to one point in the direction your hand is moving. But what happens when your hand moves faster than the rings are moving in the water? The rings can never reach the point where the next stone is being dropped. The overall effect is to create a V-shaped disturbance in the water. The angle of this V-shape depends on the speed of which your hand is moving. This effect is occurring in a 2D plane with water, but it can also occur in 3D space with sound. Sound, like water, is made up of waves. Water waves are regions of high and low pressure made up of water molecules, whereas sound waves are regions of high and low pressure made up of air molecules. When a sound is observed, it is due to a disturbance moving the air molecules causing a sound wave. The sound wave propagates in a similar way to the water wave, but in 3D. If you now imagine clapping at regular 1 second intervals, you will produce concentric sound spheres. Spheres are produced instead of rings as the sound can propagate in 3 dimensions. If you are moving while clapping, the 3D sound spheres are bunched up in the direction you are moving. This is called the Doppler effect. How bunched up or spread out sound waves are determines if they correspond to a high or low pitched sound. The spread out regions are low pitched like a double bass, and the bunched up regions are high pitched like a violin. This means that the area in front of the clapping hand will correspond to a higher pitched noise. You can observe this when an ambulance drives past you with its siren on. As it comes towards you, the sound waves are bunched up, so it sounds high-pitched, and when it moves away from you, the sound waves are spread out, so it sounds low-pitched. If the clapping hands could move as fast as the speed the sound waves propagate through the air molecules, all the sound wave spheres would meet up at one point. When the hands move faster than the speed of sound, a 3D cone-shaped disturbance is created. The edges of this cone, known as the boom carpet, are regions of high-pressure sound waves and will result in the observer hearing a loud noise, like an explosion. This noise is a sonic boom and occurs in aeroplanes, which can travel faster than the speed of sound. Now we have covered 2D water waves and 3D sound waves, we can move on to Cherenkov light. Light, like sound and water, is made up of waves. These waves are electromagnetic waves. When a charged particle moves, it causes a disturbance in the medium it is travelling in, releasing electromagnetic waves. Imagine the charged particles to be like the falling stones or the clapping hands, releasing at regular intervals these electromagnetic waves. Again, the faster the charged particle moves, the more bunched up the waves are. Cherenkov light is produced when the charged particles travel faster than the electromagnetic wave in the medium they are travelling in, when the particles are travelling faster than the speed of light. You are constantly told that nothing travels faster than the speed of light, but this isn't entirely true. It is correct that light travelling in a vacuum is the universal speed limit, but if the light is travelling in something else, like our atmosphere, it has to slow down, meaning other particles can overtake the light. When this occurs, a cone of electromagnetic waves is produced. The electromagnetic waves are built up along the edges of this cone, causing the blue Cherenkov light to be produced. This is a light equivalent of a sonic boom. Now that we understand how Cherenkov light is produced, how is it related to the CTA and gamma rays? As mentioned earlier, gamma rays cannot pass through the Earth's atmosphere, so are absorbed. They are absorbed by atoms in the atmosphere, producing electrons and positrons. Gamma rays have extremely high energy, so resulting electrons and positrons travel faster than light in the atmospheric gas. This produces the Cherenkov light, which is detected by the CTA. So by detecting Cherenkov light using the CTA, we are essentially detecting a gamma ray that has entered the Earth's atmosphere.